Hey everyone, it's Mr. Canfield coming at you with a light on because it's night outside. This is better. This is better. All right, Mrs. Canfield and her good ideas. All right. So today is the much anticipated volumes of revolution, and we're going to look at some other volumes as well. So the big deal with this is if we take some function, also this video is going to be in several parts. So you're going to have part one, it's going to be the intro. Then you're going to have part two, disk. All right, so the four main parts that we have to look at with volume are an introduction, just talking about the general idea. Then we're going to look at something called disk method, washer method, and then there's an alternate way that other kinds of volumes that we find. Hey, this is Canfield from the future. We actually don't get to part four in this video. We're going to get to part four in the next video. So if you are looking to skip through parts of this video, I'll try to have the part name at the top for a little bit. So I spelled disk wrong. No, I don't know. I think it's with a C, because disk with a K is when it's computers, like a hard disk. Anyway, that's not important. What is important is how this thing works. So take some rando function. Let's say the function looks like this, okay? This works way better on the computer. If you just type in disk method animation, it really, really helps. Because what we're going to do is we've been able to, let's say we're going from, I'll just call this A, call this bay. Let's say we're going from A to bay, and we're just finding that shaded region. We've done that a billion times, right? We know that if we're calling this f of x, then we can say the area is just equal to the integral from a to b of f of x dx, right? And then we have ways to do that and to find that. But then what we could do is, what if instead of trying to find this area, I wanted to take this curve, and if you think about the x-axis kind of as being an axis of rotation, taking this curve and actually spinning it around the x-axis, what kind of shape might we get, and can we find the volume of said shape? So let me try to give you like a three-dimensional view really quick. So like, I don't know if you can gather what's going on here. If this is our, so I'm just kind of looking at an angle here. If we're taking this and spinning from A to B around the x-axis, well, think about spinning a point. What kind of shape do we have? If we spin either of these endpoints, we're getting a circle, right? And if we spun anywhere else, we'd be getting some kind of circle. The problem is, the radius here is one thing. The radius somewhere else is going to be something else. And let me try to draw what this shape might look like. This kind of shape might give us a vase, but we're trying to find like the filled in, like what if this was just a solid piece of material? So the thing is, this volume is not that hard to find if we break it down and think about it at its fundamental level. So instead of thinking about, oh, this bizarre shape, let's think, well, what if I just take a single spot and like just make a really, really tiny rectangle, which, that should call back Riemann sums for you. Take a little tiny rectangle and spin it around. We're gonna have a circle, but it's gonna be a circle with some width to it, right? If that's like our x-axis going through the middle, this is going to give us, if you think about this, this is a cylinder. Normally we look at cylinders like this. Oh, it's a can, woo! So the way that we would find the volume of a cylinder is, if this is our cylinder, a cylinder is just a bunch of circles stacked on top of each other. So the volume of a cylinder, we really just take the area of a circle, which is, we'll do that in a second, and we just multiply that by the height of the cylinder. So the way we find the volume of a circle is we take pi r squared, right? Well, whatever that radius is, we do pi r squared, and then we multiply that by the height. And that's the volume of any cylinder, any right cylinder. So that's uniform width though. And so that means uniform radius all along. It's the same radius every time. What happens when the radius changes? Well, if you recall, with the idea of Riemann sums was we could take a rectangle, add up an infinite number of rectangles, boom, integral. We squish them down, we make them infinitely tiny, and we get an infinite number of them in there, and the result of that is we can just take an integral. So if I could figure out how to make an infinite number of little cylinders here, or an infinite number of little circles here and multiply it by their height, then we'd be good. And so it turns out what we can do is the area of one of these, well, let's think about it. Let's think about a single circle along our vase here. How do you find the area of a circle? Pi r squared, right? Well, what would the radius be? The radius is the distance from the axis to the outside. So on this side view, this is our axis, right? This is our edge. This right here would be the radius. Well, hey, what's that radius? It's just the distance from the x-axis up to our function, which we call f of x. So in this case, our radius is just f of x. So the volume of, or sorry, the area of one of these circles, I could say is pi times f of x squared. That's the area of one of the circles. And if I then wanted to take that circle and add it to all the other circles that I get here, all I have to do is integrate that, and now it's volume. I don't remember if we've talked about this, but the integral of area is volume, I guess, plus c. This is more of a thing that we'll notice happens. It's not, you don't need to like memorize that or anything, but it makes sense if you think about it from like a, and there's some modification to it that we have to do, but if we think about in general, like, volume adds another dimension, and when we're integrating, we are going, we're reversing derivatives, so we're adding on exponents. Anyway, I can say the volume formula here is, that pi in there is kind of weird. Let's bring it up front. I can say pi from the beginning to the end, which was a to b, right, from up here earlier, of our radius squared dx, pi r squared dx. And so knowing this formula, you might be like, well, where'd the height go? The height came from, remember that the height of a cylinder is it's this way, right? This is the height. So that's adding up the infinite number of slices that we have. So that's part one. That's our explanation of the concept. So then we can go and look at some specific examples. So here, Stu leads us to a nice example of the curve y equals x squared. And it says y equals 0, x equals 2. So it brings in this line and it brings in x equals 2. So it's this shaded region right here. So let's, you know what? I said I was going to do this. So part 2. So we're going to look at number 1. It says y equals x squared, y equals 0, x equals 2. And let's say the summed up version of this is find the volume of solid formed by the region bounded by those guys. So find the volume of the solid bounded by, find the volume of the solid formed by the region bounded by those guys. So by this region rotated around the x-axis. Depending on what we pick for our axis, the problems become wildly different. But let's start out with this shaded region. So y equals x squared is this doohickey, right? So here's y equals x squared. Then, so, and I'm going to try to color code these. We got y equals 0. So they intersect right there. That's going to be like a closing off place of our region. And then, I guess I'm going, cotton candy today a little bit. So x equals 2. Now, x equals, that's a vertical line at 2. So where's our closed off region? So a lot of times they'll call this region R. But that letter actually is going to be, that might be confusing a little bit later. Because we talk about radius and radii with these, and that's also an R word, so we don't want to use more than one. Sorry, I didn't mean to bring up the R word. Okay, so we have this orange region, and it says rotated about the x-axis. So that's going, it's going this way, right? And so we want to find, just if we can find the radius just goes from our axis up to the curve, right? That's our radius. Again, why I was like, maybe we shouldn't use the R letter there. If that's our radius, well, that's just 0 to the function. That's just f of x. So I can say that if we go from, 0 was an endpoint, and our other line there, that's another endpoint. So we can go from 0 to 2, and it's pi r squared, right? So pi r squared will go from, we did that, and we just said it was our function, our f of x, so that's x squared. So instead of writing pi x squared squared, you could write pi from 0 to 2, x to the 4th, don't know why I'm putting that in parentheses now, dx. And this is an easy integral. We can do that by hand, we can get the number. But if you remember, I know I've said this in class, I don't know if I've said it in a video though, we're kind of at the point in the year where doing integrals by hand is passé. Okay, you may notice I did not put the pi on the front because I don't want to find out what 6.4 pi looks like. It's this garbage, right? Or I could just write, and that's the exact answer. So I could, the light, there we go. I could write 20-point garbage, or I could write 6.4 pi. You know, on the AP exam, they're both right. This one is cleaner, and if I have to do any further calculations, this one's a lot easier to work with. If you want to take 6.4, turn it into a fraction. Let's say we got the answer. I did the work at 6.4, go to math, and that very first option there, You just click enter, it takes the answer, converts it to a fraction, boom, 32 over 5. So I could even say 32 pi over 5 if I want to be super fancy. I'm not given units here, but if I was, it's a volume. What's the units for volume? Units cubed, right? So I could say units cubed. Okay, so I just rolled my rolly chair onto my big toe. All right, I'm fine. Okay, so now it says, now let's rotate the region about the line y equals 4. Let's not and say we did. We're going to come back to this one. You'll notice that the shape winds up being different here. Well, we can talk about that. But what would happen instead if I took a function What if now we take the same shape, the same picture, and instead of rotating it around the y-axis, sorry, I just kind of gave it away. Instead of rotating it around the x-axis, we're going to rotate it around a vertical line. So same region, exact same shape, pretend the drawing's the same. It's totally not. But now we're taking this region. I'm doing one part D right now. So I think one part A and one part D go a little bit better together. And then we'll look at B and C for, that's gonna be part 3 of the video. So now I wanna rotate around x equals 2. So if we picture that, this is x equals 2. That means that this is the axis, and this is going to rotate around. So if you think about the kind of shape that would be, it's going to be like that on both sides, and then kind of like curved, almost like the top of a circus tent or something, or an upside down funnel. But I guess it goes to a point at the top, so it's a pretty lousy funnel. You got to cut the end off. But anyway, the radius here, well, that goes from our axis out this way, right? And so we're spinning sideways. So whenever we're spinning this way, around the x-axis, we use x's. Looks like I wrote a G. If we're ever spinning sideways, we use y stuff. And we'll get into that a little bit. This radius right here, I could say this radius goes from the curve to 2, but I wouldn't be able to use the y value of this curve. I would need to use the x value of this curve. And it's not really fair to say it's x minus 2, because I don't know which x value as specifically. So what I can do, well, also this 2 right here, it's every x value ever. This has every y value kind of built in. What we've got to do is we got to take the function, this y equals x squared, and we need to convert it to be solved for x. So when I take the square root of both sides, I get x equals plus or minus root y. I'm dealing with the positive half. So I just need to say x is equal to root y. So how far apart are these two? Well, here they're closer. Here they're pretty far away. What we're going to want to say is our radius is going to be equal to, usually when we write distances out, we write final minus initial. So we end up at 2. We start at our curve. So our radius is going to be 2 minus root y. Finding the radius is the hardest part of these generally. So if that's my radius, and I know that pi r squared h, that's my formula, and h turns into my integral, since this is my circle, we're not stacking our circles horizontally this time. Now we're actually stacking our circles vertically. So I don't want to put 0 to 2. I want to make sure I put whatever this y value is and whatever this y value is. So the y value down here is 0. But what's the y value at the top here? Well, let's see, if x is 2 here, what's the y value of our curve? 2 squared is 4. So this integral is going to go from 0 to 4, pi out front, 0 to 4, and our radius squared, and we're going to have a dy at the end. And our radius is this 2 minus root y. So this one's not as easy to do by hand. It's still definitely doable by hand, but again, why bother? I mean, sorry. It's a good exercise to do integrals by hand. Now you totally could put y's in here and do it. As long as you're consistent here, it doesn't matter. Now, what I typed in here is wrong. This is gonna give me the wrong answer because I forgot to put the squared around my function. So, little trick, instead of having to go in and, I gotta open up a new parentheses, type the whole thing again. No, close the parentheses, now put the squared. So instead of doing that, what we can do is, I was gonna try to have Maeve type it for me. All right, so let's say we go in and we make a mistake. We get to the end. We could have even hit enter and gotten some number. This is gonna be a, what is this garbage? Is it, how am I literally getting the exact same answer? All right, we're gonna say that's gonna be a coincidence. Hold on, I gotta see this really quick. If you're not interested, just skip past where I graph. So this and this, from 0 to 4, they get the same answer? I find that hard to believe. So this, if I go from 0 to 4, these both are supposed to have the same area. So this guy does that, then this guy does. Oh, and he goes a little bit lower than him. But they have literally the same answer? That's, oh my goodness, my poor little brain. Okay, so anyway, so, oh no, they're different after 6 decimal places, they're different. Okay. All is right with the world. But anyway, let's say, oops, I meant to fix it. Well, so we can go back and get it, and then if you push second and then delete, you'll notice it says INS there. The cursor changes. I'm now inserting things instead of overwriting things. So that lets me go in and, oh, no, don't eat the battery, Maeve. Let's just go in and fix things. So that's good to know that if this was an AP question, you'd get it right even if you did it wrong. Okay, so now we got to look at part 3. And this is going to be the longest part. So now, what if we were to take this same shape and now we're going to rotate it. This was 4, right? What if we rotate that around y equals 4? What does that look like? And if you think about it, well, this end here, it's flat, right? It's going to spin around. It's going to make a cylinder. But what happens here? Well, this is our axis in the middle, right? This is y equals 4. I'm off screen. This is y equals 4. So if that it's going to be like, oh wow, that's really bad. But it's going to be some like, it's almost like a cup, but with like a really weird like curve to it. And our shaded region was this, right? So we're actually looking like, hey, how is this gonna be? So it's gonna be like filled in all the way around and like have a hollowed out piece on the inside. So how in the heck am I supposed to find this volume? Well, the way that we do it is the same thing that we did before. But instead we say, hey, take the whole cylinder. So take the whole cylinder and then subtract out the empty space. So find the volume of the empty space, find the volume of the total, and then subtract the empty space away from it. So the way that we're gonna do that here, well, how could I find the volume of this whole cylinder? Well, the radius for the whole cylinder goes from our center, or from our axis, out to the farther out curve, right? In this case, the farther out curve is the x-axis. So in this case, we call this big R usually. We could say big R is equal to 4. So I could say, oh, take the integral from 0 to 2 pi r squared dx. And our radius this time is going to be 4. You say 4 minus 0. And then we'll take away our other one. Still going from 0 to 2. We just got to find the radius of this guy. And the radius of this one is going from our axis down to our curve. And so in this case, we'd say our radius is 4 minus our curve, which was x squared. So Maeve's trying to point something out though. You don't need to write two separate integrals if they have the same constant outside and their bounds match and everything matches. We actually can write this as one integral from 0 to 2 and say it's 4 squared minus 4 minus x squared, right, dx. And this will give me this minus that, which is the volume that we actually care about. So I can go in, I can typity type, boom, 0 to 2. Remember, I'm not writing pi. Wait, 4 squared is 16. Why don't I just write that? In general, the less buttons you have to press, the better. So like cleaning up a 4 squared and writing 16 instead, usually going to save you heartache in the long run. So 14.93 repeating. So I can say, wait, I can say, yeah, 224 pi over 15. Oh, I'm off screen again. So that's what I got. And if I remember correctly from looking at his paper, 224 pi over 15, he got the same answer as us. Cool, Stu. Cool. So one more rotation to do, but it's likely going to be washer again since I'm talking about it now. So now we're taking our region, and we're rotating it around the y-axis, I'm guessing. Yeah, y-axis. So about the y-axis. So now, I guess the y-axis is funny. Hold on, let me give Maeve back to her mommy. All right, so if I'm taking this and going about the y-axis, that's taking this region and it's rotating it this way now. Oops, did not mean to write on the paper. So now, since we're spinning sideways, we're gonna need to deal with y values. So we're going from low to high. Well, the low is 0, the high was where these touched at 4. We know there's gonna be a pi. And similarly, we're gonna have to find out our bigger radius. So that's gonna be big radius minus little radius, dy. Excuse me, so the big radius it's just going from the axis to x equals 2. So our big radius is just going to be 2. Our little radius is going to go from 0 up to our curve. And so we can say that that is, remember we want to do final minus initial, right minus left. So we're going to want to do, this is, we said this is what, square root of y, I think? Minus is, oh, minus 0, yeah. So we take big R squared minus little r squared, have the pi out front, go from 0 to 4. I can type this in, get an answer. Now, before I would do that, honestly, this one especially, 2 squared is 4. Root y squared is y. Something that it's easy to kind of overlook is that oftentimes these integrals look very simple. Just because the integral looks simple doesn't mean it's like, this is a pretty complex scenario it's describing. It just so happens that this is the area of it. So if I go in, this is going to give it to me. I get exactly 8 with a pi on the end. So 8 pi is this weird looking bowl thing. And so those are, you know, washers and discs. We can run into any one at any time. We're never going to know which one until we draw the scenario. So I've already got this first one drawn out here because we did this together in class, and that was before I filmed this video. But this first one takes the line y equals 2x, and I graphed it out. You may just want to use your own paper. I think it makes life easier. But we're taking that, and we're spinning it around the x-axis. Well, the way how you know it's a disc or a washer is a disc, the shaded region of a disc is connected to the axis the entire way. There's no gaps. The reason we had to do washer was in a washer, there's a hole in the middle. If there's a hole in the middle, that's when we have to do 2 different radii and subtract stuff out of the middle. So with this one, since we're going from, looks like 0 to 3, our radius is 2x. So it's literally just go from 0 to 3, throw the pi out front, radius is 2x squared, boom, you got 36 pi. Here's the crazy thing. If I take this same shaded region and I spin it around the line y equals 6, it changes the problem. Because now I'm taking this and I'm spinning around y equals 6. Well, now it's not touching the axis the whole way, so I'm going to have to do big radius minus small radius. So if I go in, let's see. Well, we're still going from 0 to 3. Still have a pi out front. Know that I have that empty space, so I'm going to have to do one radius minus the other radius, dx. So, well, farther radius is our axis to the edge. In this case, that's 6 to the 6 to 0, so it's just 6 squared. And then our other one is going to be 6 minus our line, just 6 minus 2x squared. So if we go in and we can form this out, simplify it, all that good stuff, but we don't need to. We can just type it into our calculator, get a number. So I'm going to actually forego typing these into my calculator. This is an example of setup, but do not evaluate. Those are AP questions. They like to say, hey, set it up, but then don't find it because we don't care. I love, like, a lot of higher maths, they'll be like, so they'll spend a lot of time and they'll spill a lot of ink proving that there is an answer. And then you're like, so what's the answer? And I'm like, I don't care. So I just care that there is an answer. So for C, now if we spin it around the line, y equals 8, well, it's still this, so now we're going around y equals 8. We still have, this is 6 right here, right? Here's 8. So now we're spinning around y equals 8. Works the same way though. So what's the radius? Well, one of our radii goes from 8 down to the x-axis. So one of our radii is 8. We're still going from 0 to 3 on the x-axis. The other one is going to be, well, our axis is 8 down to our line, which is 2x. It's not terribly different. And so you might be able to see whatever I put there, I'm going to be able to set it up the same way. Just our line goes there. And that's just for this scenario. It's not going to be for every scenario. But part D of this says, hey, now take it and go around the y-axis. And so now we have to be careful. Anytime we change the direction that we're rotating, stuff gets real. It's not that intense. All right, so we have this region, right? And now we're rotating it this way. So, oh, there's space, right? It's not connected the entire way to our axis. So if there's ever space between your axis and this shaded region, that tells me washer. Oh, I don't know the bounds anymore because I got to do y stuff. So we're going to have one minus the other. dy. This line is 3, right? And we got to find out our low y value, our high y. Well, our low value is 0, and our high y value is wherever these two touch, right? And this is 2x, right? So 2 times 3 is 6. So we know that we're going from 0 to 6. Let's find our two radii. Big radius. Did I say radius? Here's the radius. So here's our big radius. It's just 3 down to 0, so we can just say our big radius is 3. And then our small radius is 3 down to our line. Oh. I cannot write 3 minus 2x here because I need to make sure that I'm in y territory, not x territory. So instead of saying 3 minus 2x, I got to take this y equals 2x and solve it for x first. Some very complex steps happen there. So you can write it 1/2 y or y over 2, whatever you're more comfortable with. They're identical. Twins? No, just kidding. So 3 minus 1/2 y squared. And now this would give us that region spun sideways. I know I'm going through rapid fire. There's just so many examples and I want to get through all of them. Now we're taking it around the line y equals 3. Nope, x equals 3. So same region. This was x equals 3 right here. This is very similar to our first example. So now we're spinning around the line x equals 3. It's in contact the whole way, so I can set this up as a disk. Going from 0 to 6, right? Low y to high y. And our radius is just going to be this distance here, which is going to be 3 minus 1/2 y. Boom. And then we get to part F. Now we're going around x equals 4. Same region again. But now spinning around x equals 4. So the region is the same, so our bounds are the same. Still going from 0 to 6. We're going to have big radius minus little radius. Big radius this time, 4. My brain got stuck for a second because I'm like 4, oh, it's 0. Oh wait, but this, and it's anywhere along here. So it's gonna be 4 minus our function. So that's that's the farther away run one. Here's the closer one. Right, so there's our big R, here's our little r. Little r is gonna be 4 minus, oh wait, this is 3 all the way along here. So it's 4 minus 3. I could just write 1. Or I could write 4 minus 3 and also be correct. It's a mouthful. But if I lose you on any of this, please just let me know. I obviously can't, like, right now I can't help you in my time, but in your time I can help you. So if you like email me or, you know, cash me outside, how about that, or whatever, then we can get you the help that you need. All right, and hey, if you don't want to ask me, ask somebody else. Chances are you know somebody who knows calculus. And if you're like, no, I don't, well then, never mind. All right, y equals 1 plus root x. Well, 1 plus root x is that top half of the parabola starts at 0 normally, so that 1 plus tells us to move it up 1. So it's that. And y equals 1 is that, and x equals 4. So I should find, so here's my shaded region, right? I should find these points. I'm guessing I might need them at some point. This one is 0, comma, what, 1 because of that? So 0, 1, this is going to be 4, 1, right? And this will be 4, comma, whatever the curve is at 4. So if I plug a 4 in there, I get 2, plus 1, I get 3. I'm guessing that those will be important somewhere in this problem. Okay, so let's see. First one says to go around the x-axis. So that's this guy right here, right? So if I'm doing x-axis, that's, well, we're going from 0 to 4. We got a pi. And there's space between the shaded region and our axis. So I'm going to have 2 separate radii. So looks like our big radius is going to be the outside curve down to our axis. So the outside curve is 1 plus root x. And we normally would say minus the axis, but the axis is 0. So we say minus is 0, so we'll just leave it. Then our second one is going to be from 1 down to our axis. And there's our first one. Now it says go around the line y equals 3. Oh, so that's this line up here, right? So that's here. So then our big radius is going to be that one, right? So that's 3 minus 1. Same everything else. So 3 minus 1, it's 2. It's going to be 2 the whole way. Our inside one is going to be 3 minus our curve. So be careful about your parentheses, you know, or, you know, distribute the negative before you write it or something like that. Just knowing that we got to carry things carefully. So we could say this is what, 2 minus root x, that'd be the same thing there. All right, now it says the line x equals 3. Well, if we're going around, nope. Here we go, the line y equals 1. All right, so if I'm going around y equals 1, this is part C, well, we're connected to the axis the whole way, so I just need a disk then. We're going from 0 to 4, right? 0 to 4, radius squared. The radius is our curve minus our axis of 1. Wait, curve minus our axis of 1. 1 plus root x minus 1. So we could rewrite this as just the square root of x squared, which turns into x. All right. D says go around the y-axis. So now I'm taking this going around the y-axis. So our big radius here is going to be the y-axis up to the line, and that's 4. So I'm going to write the radii first, and then I'll figure out the rest. Remember, we got to deal with y stuff. So, oh no, this is going to be the harder part, isn't it? That's what I said earlier, right? The radii are the hard part. So first one's easy, it's 4. Second one, though, I'm going to have to do some work. So, because I got to do 4 minus our curve, that's going to be our closer radius. Right, because we're going, there's our big one, and then there's our short one. So, I think I just said some wrong words. So our big radius was our 0 out to our 4. Our small radius is going to be 0 out to our curve. But our curve is in terms of x right now. I need to switch it around and make it in terms of y. So if I was going to do that, I'm going to get this and I'm going to solve it for x. So I'll subtract the 1 from both sides first. And I'll square both sides. So I get x is equal to the quantity y minus 1 squared. So that's going to be my small radius. I'll do that minus 0. Oh, and make sure you have the pi on the front. And our bounds, 0 to 4. No, our bounds need to be y values. So we go from our low value, which was 1, to our high value, which was 3. Okay, that was our y-axis. 2 more on this problem. X equals 4. All right. So if we're going around x equals 4, taking that around x equals 4, it's touching it the whole time. So I just need one singular disk, low to high, y. Make sure we're in y's, though we're spinning sideways. So if this is our axis, we go until we hit the curve. So axis minus curve. So 4 minus curve, y minus 1 squared. So this mess, type it all in, boom, get an answer. And our last one, x equals 6. Okay, I'm just going to redraw it real quick. Now we're going about x equals 6. So let's find our 2 radii, because there's some empty space there. Our first radius goes from 6 to our curve, right? So big R is going to be 6 minus our curve. And then little r is going to be 6 minus that vertical line there, which was 4. Oh, it's 2. 6 minus 4 is 2. So now I can say that my pi, going from 1 to 3 still, 6 minus y minus 1 squared minus 2 squared. Right, 2 squared is 4. So, okay. So these are formulaic. They all work the same way. You just basically, you have to figure out what scenario you're in. And once you figure out what scenario you're in, then you know what type of formula to use. And like geometrically, hopefully it's making sense to you, like why we're using 2 areas versus 1. Because that's the key thing to figure out. If you're able to gather why, all right, I need to actually talk about the math and not just do it. So y equals x squared is this curve. This will benefit from using another color. Y equals cube root x. This, if we solve this really quick for x, this will illuminate a little bit for us. We can cube both sides to do that. We can say this is x is equal to y cubed. So this is going to be like, oh, this is going to be like an x cubed graph, but like on its side and flipped over. So instead of like an x cubed graph that does that, right, it goes like that, this is going to do, we turn it on its side and then flip it up. It's going to be something like that. And so our shaded region is going to be that, right? Yeah. So I'm filming this around Halloween. That's not why I'm using these colors. We need to find the intersection points. G, 0, 0. Ugh, how nice. The other one is another nice one. When does x squared equal the cube root of x? Well, it equals it when it's 0. There's only one other number. Only one other number. It's at 1, 1. So we have 0, 0. We have 1, 1. So for a lot of these, our bounds are going to be the same, x's or y's. So if I'm going around the x-axis, oh, there's empty space there. So we'll go from the beginning to the end, throw the pi. Now our big radius minus our small radius, dx. All right, big radius goes from our axis to the very edge. Oh, that's the orange one. That's cube root of x. So that's going to be our first one, minus axis to the inside curve. That's x squared. So here's the thing. If you ever do this and you get a negative number, that most likely means that you put them in the wrong order. Because if we reverse these, we're going to get a negative number. Instead of taking the big minus the small, we did the small minus the big. So that's generally what happens if you get a negative number. All right, let's see. B wants us to go around the y-axis. Okay. So that's this way. So like now the x squared is our outside curve if we're going to our y-axis. Let's see, low to high, it's still 0 to 1, just now we're talking about y's. So and since this doesn't have a flat edge anywhere, chances are this is going to be a washer for every single one because there's no way for it to be in contact with an axis the whole way. So let's see, y-axis. Oh, wait, I didn't solve for that. Square root x is equal to root y. Okay. So I can say root y is my big one, and then y cubed is the little one. Remember that squaring a square root makes it go away. So I could simplify this and write a y, and I could simplify this. This is saying y cubed squared, which means y cubed times y cubed. Or you can multiply the exponents. I really like these pens. For me, they're fun to write with. Hopefully me having fun writing is not getting in the way of me being legible. I did fail handwriting in first grade and thought it was awesome that I failed it. All right, so now we're going around the line y equals 1. All right, so now our big radius goes from our axis to the very far outside. So in this case, big radius is 1 minus our curve. That's x squared. And I looked back at my color coding a minute ago. It really does help me. I was like, well, that's the black one. Oh, right, that was x squared. And this was my orange one. I still have the marker here. Use the color. Come on, dum-dum. Okay. And then my little radius goes from my axis to the inside curve. So little radius is going to be 1 minus cube root x. So now you just got to, that one goes there. That one goes there. Nope, not plus, minus. dx, pi out front. We're still going from 0 to 1. Okay. All right. Oh, good, we get to do a different problem. I'm like, how many more of these can we do? If you are getting to the point where this is tedious and you get it every single time, I'm really happy about that. I would rather these be tedious than these be a challenging puzzle every time. Okay, y equals e to the x. Well, e to the x doesn't start at 0, it starts at 1, because e to the 0 is 1. And it actually has a horizontal asymptote, right? Like that. But then it says x equals 0. It says y equals 0. Right now, this is not enough. We wouldn't know what the region is. It could be the left side, it could be the right side. But then it brings in x equals 1. And we're good. So now we got a shaded region. So if I'm taking this around the x-axis, oh hey, it's touching the whole way. So since it's touching the whole way, we can just do a disk. There is no inside and outside radius. It's just touching the whole way. So for A, around the x-axis, we can say it's pi from 0 to 1 of e to the x squared dx. Let me just take a moment. If we multiplied this exponent, what would we get? We don't get e to the x squared, we would get e to the 2x, right? So just be careful with that. The only way we could get e to the x squared would be as if it was e to the x raised to the x after that. Then we would multiply the x times x and get x squared. All right, now we're going around the y-axis. So we gotta be careful. Around the y-axis, there is some gap between the axis and the shaded region. So what's the lowest we get here? The lowest we get is 0. The highest we get is, well, when x is equal to 1, that's e to the 1. So that's gonna be an e. So we got pi out front, right? Because this is 1 comma e. And then we're just gonna do big radius, small, well, y-axis, okay, so big radius is just that big space. It's the same the whole way, so it's just e. Small radius is just gonna be the inside out to this other curve that we hit. Uh-oh. I see a little bit of a problem. I don't know if you see it. What's our small radius down here? That's not quite right. So this isn't going to work. This isn't going to fit quite the way that we thought it was going to. This formula is only going to work from here. It's going to take care of this. My small radius being 0 to our curve. Oh, and our curve, I got to go in y's, right? Y is equal to e to the x. Well, to rearrange this, we'll ln both sides. And when we do that, we get ln y is equal to x. So this curve is ln y. So 0 to ln y is my little. So I can't go from 0 to e. I can only go from, this is 0 comma 1. I can only go from 1 to e. And that gets me this portion. That gets me this part of it. But how do I get this bottom part here? Well, I could take this whole thing and then add on This is just a straight up cylinder. There's no weird curvature or anything. I can just take all this plus a cylinder of radius E and a height of 1. Pi r squared times 1. There we go. That takes care of the rest of this. So, straightforward, 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 weird out of nowhere. All right, so then if we're gonna take it around the line x equals 1, let's see if anything else weird happens with that one. I don't know, it looks like we're just touching it the whole way. So if we're going around x equals 1, yeah, we're just in contact the whole way. So, oh, no, weird stuff happens again. Because we're not going from, our 1 from 0 to E. We don't hit the curve everywhere. After a certain point, we start hitting this. We just go back and forth between these two and we're stopped. So that means that we're going to have two different things to add together again. So our first one is going to go from 1 to E, and our second one is just going to be but it's in contact the whole way, so it's just going to be a singular radius, right? And we're going to have to add it to this bottom chunk down here again. So pi times our radius squared times the height of it, and the height of it is 1. And so, oh, wait, the width of this is 1, it's not E. Sorry about that. So we're just going to add a pi to it. Pi. So anyway, this one, though, is just going to be, we're going around y equals 1. It's going to be 1 minus our function, right? So 1 minus our function, 1 minus ln y. And then I was definitely thinking about it wrong. I was saying, hey, take this thing and go around the y-axis, but we're going around y equals 1. In this case, it doesn't matter because the radius is still 1 the whole way. It's just spinning it around that way this time. So it'll still be pi times 1 squared times 1. Woof. All right. So that's those. I've been filming for a long time. I think I need to cut this video here. We'll come back to part 2, to part 4 next time.